Now we are still looking at how to add all the terms in a sequence up, but in the last section we were doing an arithmetic sequence. This time we are doing adding all the terms in a geometric sequence. Now this formula only works for a finite geometric sequence. There is a way to add the terms in an infinite geometric sequence if it meets certain conditions, but we're just going to be focusing on the finite ones here. So the information we need to find the sum, that's what the S sub n stands for. We're going to need the first term in the sequence. We need to know what R is, which is the number that indicates the multiplying pattern. Like if you're multiplying by 3 over and over and over again, then R is 3. And we need to know how many terms there are. So if we're adding 10 numbers together, then that's what n would be. Up here, you would put 10. So when you plug these values in, the simplifying can be a little bit tricky because you are going to have a fraction and you're going to have some big exponents going on. But that's basically it. Plug in these three numbers and reduce. These variables have been defined in other videos of the notes, but I just wanted to rewrite them, a brief description to remind you of what they each refer to. So here's our first example. We've been given a geometric sequence and we want to find the sum of all the terms, which is also indicated by the fact that they put plus signs in between all the numbers. Well, the first part is the easiest. If we need to know a sub 1, they gave me the first term in the sequence, so I know that it is 3. To find R, pick a number and divide by the number in front of it. It doesn't matter which one you pick, as long as you have two numbers right next to each other. So for example, if I pick 6 and divide by 3, or 12 and divide by 6, whichever numbers you pick will be fine. So I'm going to pick 12 and divide by the number in front of it, which is 6. So 12 divided by 6 in this case. And then that tells me that my R value is 2. Now this is one that was pretty easy to figure out even just from looking at it. 3 times 2, 6 times 2, 12 times 2, etc. But sometimes you will get ugly fractions. That's why it's good to know this process of picking a number and dividing by the one in front. The hardest thing to identify here is the n value because they didn't write out all the terms, so I can't tell just by looking at it. Now I could continue to fill in the missing numbers by multiplying by 2, multiplying by 2, multiplying by 2, etc. until I get to 768. However, alternatively, we can use the explicit rule for a geometric sequence and plug in the information we have to solve for n. If I'm using the explicit rule, we know that a sub n is equal to a sub 1 times r to the n minus 1 power. Well, if I treat a sub n as 768, so if that's the last term or the term I'm interested in this case, that'll be a sub n. We know what a sub 1 is, it's 3. And we figured out what r was, it was 2. And we're going to solve for that n value in this case. So what I can do here is just perform opposite operations to solve this. So I'm going to divide both sides by 3, which will give me the number 256. And then this equals 2 to the n minus 1 power. Now this can be solved using logarithms, or you might recognize that 256 is a power of 2. So in case you don't remember logarithms, let me just show you that 256, that's 2 to the 8th power. So I could write it that way instead. It's the same thing. And then one of our tricks for dealing with exponents is if the base matches on both sides, so if you have 2 to a power equals 2 to a power, then you can actually just set the exponents themselves equal. So being able to rewrite one side of the equation as a power of the same number, so rewriting, since this was base 2, rewriting this one as a power of 2, that makes an easier way to solve for the exponent in most cases. Now I just need to add 1 to both sides, so n is equal to 9. So if this happens, if you have a number equals something raised to a power, just try to rewrite the number on the left side as a power of that same number. Try to rewrite it using the same base, and then when your bases match, you can just set the exponents equal and solve from there. So now I know that there were 9 numbers total. Since we have all of our information, we can plug that into our new formula. I went ahead and rewrote this up here for reference instead of flipping back and forth on the slides. So I just need to plug in the numbers I found. A sub 1, the first number is 3. And then we have 1 minus r to the n power. So 2 to the 9th power. This is going to make a very big number up here in the numerator. All over 1 minus r, which we said is 2. So now I just need to simplify these things. You can see that since we're doing 1 minus 2 to the 9th power, you are going to end up with a very big negative. So I got negative 511 from that. And then 1 minus 2 in the denominator is equal to negative 1. So we just need to take our number, multiply it by 3, because I have negative 511 times 3. Now the negatives on top and bottom will cancel, so I can stop worrying about those. It's going to come out to a positive 1,533. Now this one was only asking us to add 9 numbers, so it wouldn't have been the worst thing in the world to just list out all the numbers and add them together, but I'm trying to show you easy examples so that when you have a harder example where they're asking you to add 80 or 90 numbers, you don't have to sit there and hit a million keys into your calculator. So please use the formula, do not just sit there and add the terms up, so that when we get to the harder questions on the assignment, you can still follow along. Now here's a second example. They've given us slightly different information this time. Now I still know a sub 1, because that's negative 1 in this case. We can still figure out r. They didn't tell me what r is, but I should be able to pick a number and divide by the one in front. So no matter which number you pick, if you divide by the number in front, in this case, you're going to get the number negative 8. So this is a pattern of multiplying by negative 8 over and over and over again. Now nicely on this one, they actually gave us what n equals. N is equal to 9. On the last example, they didn't tell us what n was. They told us what the last number in the sequence was. But for this one, now we have everything we need to plug into the formula. So again, I went ahead and rewrote the formula for easier reference. So notice that we have a sub 1, we have r, and we have n. We don't actually have to solve for any missing values in this case. We could find what the last term was using the explicit rule if we needed it, but it's not needed for this formula. So I'm just going to go ahead and start plugging in my answers. A sub 1 is negative 1. 1 minus, now be careful with plugging in a number that has a negative sign attached to it. So I need to use parentheses here to show that it's negative 8 in parentheses being raised to the 9th power. When you have negative numbers being raised to powers, it's very important that you use parentheses correctly. So the number being raised is negative 8. Put the negative 8 only in the parentheses. And then in the bottom, I have 1 minus, and then since I'm subtracting a negative 8, this will come out to 1 plus 8. So I'll just write it that way. And then for simplifying this, so same thing, your calculator will get the answer wrong if you don't use parentheses correctly as well. Since it's non-exponent, it's not as big of a deal on this one, but it will matter for even exponents. So I have negative 8 being raised to the 9th power, and we're doing 1 minus that answer. So it's going to be negative, because the negative 1's not going to change anything, so it's just going to flip the sign on my answer. So I get negative 1, 3, 4, 2, 1, 7, 7, 2, 9. A huge number. And all of this is going to be divided by 9. And now this time I don't have a negative number in the bottom, so my answer will stay negative. I got negative 149, 130, 8, and 1. So it is nice when you don't have to go through to find any of your missing values, a sub 1, r, and n. It does let you just go straight into plugging into the formula and solving. Again, this one could have been solved by just writing out the 9 terms, multiply by negative 8, multiply by negative 8, multiply by negative 8, and then adding all the terms together completely. The last thing I'm going to show here is something called summation notation. This is actually just another way of writing a series, and this can be applied to either an arithmetic or a geometric series. So this symbol here, this is the Greek letter for sigma, and it's used to say a sum, S for sigma, S for sum. So the number on the bottom is how you indicate what the first term will be. So usually they just put k equals 1 down here to say that you're starting from plugging in k equals 1, so a sub 1, and then you just keep going a sub 2, a sub 3, a sub 4. So this pattern indicates that you just keep adding 1 to that number wherever you plug the k in until you get to the top number. Whatever number is on top is your stopping point. So basically the number underneath is the starting point, number on top is the stopping point, last number and first number, and then this will define the sequence itself. So here for the bullets, I tell you that the explicit rule for the sequence is what goes to the right of the sigma. So if you're doing an arithmetic or a geometric, we've already seen the explicit rules for those. It may not be an arithmetic or a geometric sequence. It might just be a sequence that they've written a formula for. So whatever the equation is, whatever the formula is that creates the terms, that goes on the right of the sigma symbol. And then I've defined here the numbers that go on top and underneath again, the n value for the first term being added. So where do you start the sequence? Are you starting it from the first term in the sequence, or maybe you're starting it from the 5th term in the sequence? If you're starting from the first term, which is what you usually do, you put k equals 1 in the bottom. If you're starting from the 5th term, you don't want to add the first 5 numbers, then you start from k equals 5. So whatever number you have here will be the first term of your sequence that you are going to be adding together in formula. And then the last number that will be added goes on top. So maybe it's an infinite sequence. Maybe there are an infinite number of numbers, but you only want to add the first 10. Then you'll put 10 on top. Maybe the last term in the sequence you want to add is the 20th term. Then you will put 20 on top. So this is the stopping point, the last number that you add in the sequence. So here's an example of a question you might be asked to do. Like I said, this number underneath, this is our starting point. This number on top is our stopping point. And then this out here is the formula we use to create the terms in the sequence. It's our explicit rule. So for example, since my starting point is a 1, if I plugged in k equals 1, I would have 4 times 1 minus 1. So the first term of my sequence would be a 3. If I plugged in the next number, 2, 4 times 2 is 8, minus 1 is 7. And then I would plug in the next number, 3. 4 times 3 is 12, minus 1 is 11. And then I would plug in 4. 4 times 4 is 16, minus 1 is 15. And I would keep doing this over and over and over again until I get to the last number. If I plug in 15, 4 times 15 is 60, minus 1 is 59. So like I said, these two numbers, these are just indicating what the smallest and the biggest k values are that you plug in. K equals 1, k equals 2, k equals 3, k equals 4, and I skipped a whole bunch because I didn't want to write them all out. K equals 15. So we can actually solve this using our same rules as before. You'll hopefully notice that this is an arithmetic sequence because it is adding 4 over and over and over again. You might confuse it with the geometric because it looks like you're multiplying, but that process of multiplying is just what's causing it to add 4 over and over and over again. So what I have here is an arithmetic sequence. We know the first term, so we know a sub 1 is equal to 3. We know d is equal to 4. We know a sub n, the last term that we're dealing with, is 59. And we even know n actually, because n is just that number on top. So there must have been 15 numbers altogether. It's how many numbers we had, because the last number we plugged in was 15. So I went ahead and rewrote the formula for adding the sum of an arithmetic sequence here. It's the number of terms times the average of the first and the last. So add the first term and the last term, divide by 2, and multiply by how many numbers there are. This one had to be a sum question because that's what the sigma refers to. It's always a sum question. So if you see this, just know that you are adding the terms in the sequence up, not just listing the sequence out. Okay, so if I'm plugging in these numbers I got, I have n is 15. The first term in the sequence was 3. The last term in the sequence was 59. And since we're averaging those two numbers, we're dividing by 2. Well, 59 plus 3 is 62. And 62 cut in half is 31. So then we just have to do 15 times 31 for our answer. And I got 465. So this isn't a new process. This isn't defining some new concept. All it's defining is a new notation to tell you to add all the terms in a sequence up. And it can be applied to arithmetic or geometric. Whenever you see this rule, this symbol, just know that you are adding whatever's on the right-hand side of it, starting with the bottom number, ending with the top number. So that's it for our look on series.